Welcome to the module Building a Motion Model and Post-Processing. In this module, you will learn about different types of mates, how to add local mates to the assembly, and how to create a relative and an absolute values results plot. In Part 2, you will learn how to use the function builder to construct functional expressions for motors and forces. You will also learn how to create and modify kinematic plots. Along with that, you will learn how to create absolute as well as relative values plots with respect to local or global coordinate system. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. Function Builder can be used to construct functional expressions for motors and forces. Function Builder can build functional expressions using predefined segments, imported sets of discrete data points, or mathematical expressions. Let's take a closer look at each of these. Click each button to learn more. In the Segments view, the user selects both the independent, typically time, and dependent variable, displacements, velocity, or acceleration. For each specified interval, the transition from the initial to final value is controlled using one of the predefined profile curves. The profile curves that can be used include linear, cubic, quarter sine, half sine, 3, 4, 5 polynomial, and so on. As the function is constructed, the graph windows show the corresponding variation of displacement, velocity, acceleration, and jerk, time derivative of acceleration. Note that it is possible to save and retrieve functions from stored locations. The discrete set of data points can be imported from a CSV file or entered manually. Similar to segments, user can select both the independent and dependent variable. You can set interpolation type as cubic spline, linear, or Akima spline. An Akima curve is fast but will not work as well if your points are not evenly spaced. It is recommended that you use a cubic curve because it will work well even if your data points are not evenly spaced. Expression enables the construction of functions with the help of predefined mathematical functions, variables and constants, and existing motion study results. For all three cases, the function can be saved at a specific location. While using imported data points, you can use your own motion data to control the displacement, velocity, or acceleration of the motion. The data points that can be imported into SolidWorks Motion must be in a text file, TXT, or comma-separated file, CSV format. The file should contain one data point per line. The data point consists of two values, the time and the value at that time. Commas or spaces can be used as separators between the values. The file is essentially free format except for these restrictions. SolidWorks Motion allows for unlimited number of data points to be used. Note that the minimum number of data points to be defined is 4. The first column, independent variable, x, in the data point template is typically time, but other parameters such as cycle angle and angular displacement can be used as well. The second column, value, y, is the displacement, velocity, or acceleration. These values can be manually entered or imported. Let us see how to create a motor using the data points as the motor type. Click Show Me to launch a demonstration video. First, we will apply gravity in the negative y direction. Click Gravity. Specify the negative y direction. Click OK. Ensure that the time key is set to 5 seconds. Click Calculate. Notice that model position changes while calculating the study. Let's reduce the playback speed to 1/4 and play the study. Click Play. The crank will rock back and forth as gravity affects the components and potential and kinetic energy are exchanged. As there is no friction, the parts will continue to move without end. To add a motor at time 0 second, set the time bar to 0 second. Now we will create a motor that drives the crank. Click Motor. Under Motor Type, ensure that rotary motor is selected. Under Motor Location, select the cylindrical face of the crank part. The default selection for the motor direction is correct for this analysis. Under Motion, click Data Points as the motion type. The command invokes the Function Builder window. The Function Builder is often used for motors that require precise control. In this case, a spreadsheet exists relating the displacement of the motor to time. This spreadsheet will be imported into the Function Builder. Set the value, y, to displacement, and independent variable, x, to time. In order to calculate the displacement between the data points, an interpolation method must be used. There are 3 interpolation options available: linear, cubic spline, and Akima spline. A linear interpolation will draw a straight line between the data points, while a spline will create a curvature continuous path through the data points. Generally speaking, a cubic spline will over-exaggerate the curve through the data points. Therefore, we will use the Akima spline interpolation. Click Interpolation Type. And click Akima spline. Rather than type the individual values into the table, we can load them from a file. In this case, we have an Excel file which has 2 columns of numbers representing the time and displacement. Click Import Data. Navigate to and click the crankrotation.csv file and click Open. The values from the file are now inserted into the time and value columns. A graph of the displacement versus time with interpolation can be seen. Click OK to complete the definition of the profile and close the Function Builder. Click OK again to close the definition of the motor. Rename this motor feature to Motor Crank. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a motor using the data points as the motor type. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Results plots can be requested in absolute or relative values. They can also be plotted with respect to another component of the assembly. While in most situations, the default output is in the global coordinate system of the top-level assembly, it is very easy to transform the values to any other selected local coordinate system. To request the plot of absolute values, select the component, mate, motor, part, etc., in the Simulation Element field. To plot values relative to the second component, add that second component to the Simulation Element field. Note that the reference component must be selected as the second in the list to create the relative results plots. Typically, the results are output in the global coordinate system of the assembly. For some simulation components, for example, mates and motors, the default output is, however, in the local system of the selected component. To plot results in the coordinate system of a particular component, select that component in the Component to Define XYZ Directions field. The values will then be transformed into the coordinate system of the selected part. Note that the requested output coordinate system is indicated by the triad as shown on screen. Let's see how to plot relative results. Click Show Me to launch a demonstration video. Click Calculate. Click Results and Plots. We will now define the plot by forces, motor torque, and magnitude. Click the motor crank for the simulation element. Click OK. This plot will find the torque required to turn the mechanism. The plot may be improved by recording more data points by increasing the frames per second option in the motion study properties. Now, we will create a plot for the power required to turn the mechanism by selecting Results and Plots. We will now define the plot by momentum, energy, power, and power consumption. Click the motor crank for the simulation element. Click OK. Knowing the operating RPM, torque, and power, we can select the appropriate motor to drive the system. Close Plot 2. Click Motion Study Properties. Change the frames per second to 100, and then click OK. Now, recalculate the study. The torque values are essentially the same. The plot is now smoother as we have more data points. Close Plot 1. We will now create a plot to show the magnitude and direction of the force between the crank housing and the hinge of the crank. This will help us understand how these components will wear against one another. We will again select Results and Plots, and define the plot by forces, reaction force, and magnitude. In this assembly, the first hinge we defined was between the crank and crank housing. As the crank housing is fixed, the mate must transmit the reaction force. Select the first hinge mate as the simulation element. This mate must be selected from the Mates folder in the Motion Manager tree because this mate is local and is not listed in the Feature Manager design tree. Click the first hinge mate. Because the selected mate connects two parts, there are two equal and opposite forces acting in the mate. One of the two parts must be selected for the plot of this force. Select any face on the crank 1 part as the component in the Simulation Element field. Click Show Vector in the graphics window. Click OK. We will receive a warning about redundant constraints. Redundant constraints may have significant impact on the mate forces, but it will be discussed later in the course. Also, the resulting force obtained for this mechanism is, however, correct, as the redundancies present in this assembly do not have any effect on the force. Click No to the warning pop-up window. This plot shows the reaction force on the motor. Change the orientation to right. Play the simulation and observe the reaction force vector. Close plot 3. This displacement plot will show the displacement relative to the global coordinate system of the assembly. The plot will then be edited to show the displacement of the arm relative to its own coordinate system. Now we will create a plot for the x component of the linear displacement of the arm component. Select Results and Plots. And then define the plot by displacement, velocity, acceleration, linear displacement, and x component. Click any face of the arm component for the simulation element. If we select a face, the plot will be of the linear displacement of the part's origin, indicated by a small white sphere, with respect to the origin of the assembly in the global assembly system. Because the input was harmonic motion, the output will be an oscillatory motion. Click OK. We will now create a plot for the x component of the linear displacement of the arm component transformed in its own local coordinate system. Edit the definition of the previous plot and click the arm as the component to define XYZ directions. The triad on the arm component now indicates the output local coordinate system is misaligned with the global coordinate system. Furthermore, note that this local output system translates and rotates with respect to the global coordinate system as you play the motion. Click OK. The plot shows the linear displacement of the part's origin with respect to the origin of the assembly, transformed in the part's coordinate system. Alternatively, we can view the plot 4 graph as the values from the earlier plot transformed in the coordinate system of the arm. Now, we will create a plot for the x component of the linear displacement of the arm relative to the displacement of the collar. Edit the previous plot. Clear the component to define XYZ directions field. Click the collar part as the second component in the simulation element field. Click OK. We can see that the displacement has a rather different oscillatory characteristic than the displacement of the arm in the global coordinate system. The plot shows the linear displacement of the arm's origin with respect to the origin of the collar part in the global coordinate system. Now we will create a plot for the x component of the linear displacement of the arm relative to the displacement of the collar and transform the results in the local coordinate system of link 1. Edit the definition of the previous plot and click link 1 as the component to define XYZ directions. The triad on the part link 1 now indicates the output local coordinate system is misaligned with the global coordinate system. Click OK. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about plotting relative results. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Angular displacement plots can be created to measure the angular displacement of a motor, mate, 3 points, or one component relative to another component. Because the angular displacement is not a vector, only the magnitude can be plotted. Let us see how to create angular displacement plots for a motor, mates, and 2 lines defined by 3 points. Click Show Me to launch a demonstration video. Now we will create a plot for the angular displacement of the local hinge mate between the part link 1 and the cardan. Click Results and Plots. We will define the plot by displacement, velocity, acceleration, angular displacement, and magnitude. Click Local Hinge Mate 3 located between the link 1 and cardan for the simulation element. Notice the triad at the location of the hinge. It indicates that the output coordinate system is the local system of the hinge mate. Only the magnitude can be requested. Click OK. This plot shows the vertical rotation of the link 2 part, which is approximately 1.3 degrees. To explore the other options of the angular displacement plot, we will modify our existing plot rather than create a new plot. Expand the Results folder, right-click the last plot and click Edit Feature. We will create a plot to show the angular displacement of the motor. Delete the hinge mate and click the Motion Component Motor Crank for the simulation element. Click OK. The plot shows harmonic motion of the motor. The angular displacement goes from 0 to plus 180 degrees, then returns from negative 180 degrees. The slope of the graph is constant. This time, we will create a plot to show the angular displacement between 2 lines defined by 3 points. Click Results and Plots. Define the plot by displacement, velocity, acceleration, angular displacement, and magnitude. For the simulation element, click the vertex at the top of the arm, and then click the vertex at the end of the collar shaft. Then, click the circular edge of the arm pivot hole. In this case, a circular edge acts as a point located at the center of the edge. Click the Show Vector in the Graphics window checkbox. This will show lines between the 3 selected points. Click OK. The plot shows the angle between the line defined by vertex 1 and vertex 3, and the line defined by vertex 2 and vertex 3. Vertex 3, therefore, defines the center point. Notice that, in the present case, the limits of the angular motion are 85 degrees and 122 degrees, giving a range of 37 degrees. Click Save and close the file. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating angular displacement plots. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Here's a You've reached the end of the module Building a Motion Model and Post-Processing Part 2. Here are the key takeaways from the module. Click each tab to learn more. Here is a chance for you to practice what you have learned. Offline exercises are available for this module. To attempt these exercises, you must have access to a SolidWorks installation. To complete each exercise, download the self-extracting executable file from the eCourse Details page on mysolidworks.com. This file contains the sample models and exercise PDF file for every module in the eCourse.